I'm going to tell you about how we're trying to change the health system to give people more control over their own lives. Right now, the health system works when you have symptoms, you go see your physician and they try and work out what the problem is. We're trying to change it to a proactive, preventative, and personalized medicine system based on predictive systems. And I'll walk you through what we're doing on this. I can't see the age of the audience, but if you're between 50 and 74 and you're a male, 30% of you won't reach the age of 74. If you're a female, 20% of you won't reach the age of 74. And you can see from this slide, about 2/3 of the risk of dying prematurely is from cancer, slightly higher in women than in men, and cardiovascular disease. The last third is the compilation of all the other diseases. Now, with an audience this size, there's probably 15 people here that have cancer and don't yet know it. There's about 1.4 million new people diagnosed with cancer each year. Some of them have had it for years, some even for decades. So this is the change in life curves over the last century or so. The blue line is if you were born in 1900, and the arrows show where about 50% of the people have died by. So people born today obviously have a good chance of living into their 70s or 80s. We're trying to change that and understand this curve and how to shift it even more into the higher numbers. But with healthy living, we're trying to increase the healthy lifespan, not just the number of years. Now, my team sequenced the first human genome in the year 2000, but that cost $100 million and took 9 months for that one genome, and we had to have a $50 million computer to help put it together. So I've been waiting for certain criteria, and they were reached a few years ago when the cost of sequencing went from $100 million to below $2,000 per genome. Computing changed, so that $50 million computer we had, you can now buy a 1.5 teraflop card for about $100 for your PC, and it's become distributed. Machine learning's become very popular where we can actually use computers to learn much faster than humans, and coupling that with value added care. So we bought a whole bunch of these new DNA sequencers. Each one of these $1 million boxes can do 1,350 times what my entire facility in 2000 could do. So it's a huge change. We're sequencing a genome on average every 12 to 15 minutes, 24 hours a day, 7 days a week. We have about 35,000 of them now and a little over 4.2 petabytes of data. To put that in context, you could index the entire internet about 4 or 5 years ago with 12 petabytes of data. So this data set is growing very fast of just A's, C's, G's, and T's. We detected them before they became metastatic cancer. None of these individuals had the slightest hint that they had cancers. In the US, 1.5 million people get diagnosed with cancer each year. They just didn't get cancer the day before they were diagnosed. We carry cancer sometimes for months, sometimes for years before they grow big enough to cause problems. So we're finding this in about 5% of people over 50 that think they're completely healthy. So think of your health system but basically all the healthy people in this room, 5% of you have a major tumor that you're not aware of. And you'll only find it when it metastasizes or gets big enough to cause problems. We started our own clinic, we call it the Health Nucleus, to get more phenotype data to go with all the genome data we're collecting. So if you come to our clinic, we sequence your genome, we sequence your microbiome, we measure 1,800 chemicals, and we measure all the things you see on the slide. I'll take you through a few of them. We have two 3T MRIs. These are the latest ones in high energy that give us very sharp images. And we can tell the difference in the amount of water in a tissue now without any contrast media, so there's no risk. And what happens is tumors light up like a light bulb. So here's an MRI of a man in his 50s. We found a 5-centimeter tumor under his chest. And you can see on the right, the tumor lit up like a light bulb with this new MRI technique. A week later, he had the tumor removed. He only had cancer for a week, as far as he knew, and is now cancer-free. We can detect prostate cancer and diagnose it now right in the MRI, and we have now 4 cases. About 10% of the men that have come to the health nucleus discovered that they have late-stage prostate cancer, and these areas light up. So this bright area is where the cancer is, and you can see on the prostate, when it was removed, the pathology showed it's exactly where the MRI image lit up. And this man is now cancer-free. This is the kind of picture we can generate of your blood vessels in your brain, and it's very easy to see if you have any restriction in these. So up until this last year, you would have had to have contrast media to get these beautiful pictures of the brain vessels. But also, it shows up very readily, as you can see in that little knob. If you have an aneurysm in your brain, we can see it very easily. Most people know somebody that died from a brain aneurysm. They just explode like a tire blowing out, and people bleed to death in their brain. Once we know they're there, they're very easily treatable in an outpatient basis. We're finding all kinds of things in people that think they're healthy when they come in, and we're changing the definition of health. You think you're healthy if you don't have symptoms. We can determine, in fact, if you're really healthy. Here's a woman who had a softball-sized ovarian cyst that had no idea it was there. And the main problem with these is not that they're cancerous, but they're so big they can actually twist and rip blood vessels, and these women usually show up in the emergency room with massive internal bleeding. So sequencing's changed a little bit in these 17 years. Each of these boxes, and these not even the newest ones that we just got, they're about $1 million each. And each one of these boxes is 1,350 times what all of Celera could do in a year. So at Celera, we had 350 machines working around the clock. One of these boxes is 1,350 times that output. So things have changed. We have a room full of these, and we have 2 more rooms we're building out to expand it to where we would have the capacity to do 1 million genomes a year. The trouble is with data, so we've done a little over 40,000 genomes. Gene, it was a good guess. Just in terms of ACGs and Ts, that's about 6 petabytes of just ACGs and Ts. So if we had 10 million genomes, it would be an exabyte of genome data. Not to mention all the other data that we're adding to it. Right now, it doesn't matter how many nodes you have, I don't think you can handle exabyte computing here. We use Amazon Cloud. We pushed it to its absolute limits. We're one of the top 1% users of Amazon. We're up there with video streamers and porn sites. But we use a lot more CPUs than either of them do. And we wanted to reanalyze just 10,000 genomes, and they didn't have the excess CPUs to do that. So an experiment that should have taken 2 hours took 2 weeks. So trying to get up into exabyte computing, Moore's law has got to pick it up a little bit if it's going to keep up with with genome data today.
If you live to the age of 50, about a third of you won't live to the age of 74. As you can see, it's slightly worse for men. About 40% of men won't make the age of 74. And about 24% of women won't live to be the age of 74. The two biggest reasons are heart disease and cancer. So when we were thinking of setting up how to change human longevity, we decided we had to tackle all diseases, but first and foremost, predicting cancer, predicting heart disease. Medicine today is, if you have symptoms, you go get those symptoms checked out to find out if you have a disease. Sometimes that can be late-stage cancer. We're dealing with 4 women in their early 30s that have stage 4 colon cancer. That's somewhat confusing because in the US, you're not supposed to get screened for colon cancer till you're 50 years old. So we're taking new techniques for early detection. We've set up a new whole body assessment that combines the genome with multiple modality testing. And we only screen people who think they're healthy. We combine all this data with machine learning to make new discoveries about disease and how to treat it and how to prevent it. In part, we have exciting new technologies. Using the latest MRI machines from Siemens or GE, we have algorithms that can do post-processing on that data and cause a tumor cell to light up very brightly. This is just based on the water differences in tumor cells versus regular cells. So we use no contrast in the MRI. About 5% of people who get MRI contrast have a bad allergic reaction to it. We do all kinds of other predictions on your height, your weight, your BMI, your eye color, your hair color. And we wanted to go further. We wanted to see if we could predict from your genetic code your picture. So using machine learning, we did a study on 1,000 people where we took 3D pictures of them and sequenced their genomes. And here's just a couple of examples. This is a smooth subject from the photograph. And here's the prediction straight from the ACs, Gs, and Ts of the genetic code. Here's another example of a young male. Here's the computer prediction from his genetic code. The more ethnic diversity, the better. Here's a young African, and here's this computer prediction straight from the genetic code. We show these just because we have this health intelligence cycle where we're combining new discoveries in the genome from having hundreds of thousands of genomes. So we get very accurate data with actual clinical phenotype data that says whether you have cancer or not, says whether you have Alzheimer's or not. And this is a whole new preventative medicine paradigm that turns medicine on its head and will save countries billions, if not trillions of dollars if they adopt these approaches. Thank you very much.